Excuse me. I'm coming from Institute of Physics from Prague. Who knows Prague already? Who have been there? Oh, many people. Great, fine. It's a beautiful town, and I recommend you. I recommend you it not only as tourist, but you can come as well for postdoc position. If you will apply for Maria Skłodowska-Curie Fellowship, you will get a scholar, or you will get a loan higher than I have, like professor. But it is the problem in Czech Republic. We have lower loan. Okay, I will speak about THz-field induced magnetization and ferroelectricity, and it's rapidly developing topic, and I have to admit that I am quite beginner in this field because I'm expert in soft mode spectroscopy, in ferroelectrics and magnetic systems, and I will speak about it on Wednesday. But anyway, this is so exciting that I started it a few years ago, and question is, can we at all change the magnetic, or can we change the crystal structure using, great, thanks you. Can we change structure or properties of materials using light? It will be very fast, yeah, if we can have femtosecond lasers. So I asked ChatGPT, and they suggested like this. Yeah, so of course you can completely destroy the material or the whole house, but it is not our aim. Yeah, we need something helpful. And I think frequently cited paper is this one, already almost 30 years old, when this group used femtosecond optical pulses in visible range, and they illuminated nickel ferromagnet. And what they observed fast demagnetization of this system within 1 picosecond. This is really very fast effect. And they measured the magnetization using magnetoptic Kerr effect. I will speak about it next slide. But why it is happening here? They measured as well temperature. And of course, if you heat up the sample with such strong optical pulse, you increase the temperature. And because Curie temperature is 630 Kelvin, you can come to paramagnetic state, and then you reduce the magnetization. So it's quite simple effect, or not simple, but quite surprising. It's from that this group was able as well to decompose this change of temperature to change of electron temperature, spin temperature, and lattice temperature. And it relaxes, you can see within picosecond time scale. So you can really change the magnetic structure with light, but in this case, you just change it from ferromagnetic state to paramagnetic state. We would like to do something more. I will speak frequently about how to measure magnetic moment in the systems, and of course you cannot use squid or some vibration magnetometry. You need something which is fast, and this is optical method, magneto-optic Faraday effect, which is the principle is just that you have magnetic system, or you apply magnetic field in the system. You measure rotation of optical polarized beam. So if you have linearly polarized beam, you measure transmission, and you see a rotation of this polarization, and this angle is linearly proportional to magnetic field or magnetization in ferromagnetic system and the thickness of the sample, and this constant is very constant. It's not important here now, or yeah, it is sometimes of course important how strong is the effect. And frequently people measure not magneto-optic Faraday effect, which is in transmission geometry because the sample is frequently non-transparent. So they measure in reflection geometry. And in this case, it's called magneto-optic Kerr effect. But it is the same practically. You see the rotation of this optical beam polarization. Don't mix it with electro-optic Kerr effect. I will speak about it as well. In the case that you apply electric field in the sample, you will observe change of refractive index by refringence, we will see. And this by refringence will be proportional to electric field square. So here it is linear dependent on magnetic field. Here is square dependent on electric field. Sometimes you can see as well by refringence linearly dependent on electric field, but this is so-called Pockels effect. That Pockels effect is allowed only in non-centrosymmetric systems, so in ferroelectrics. So let's go further. So I mentioned with optical beam you can demagnetize system if you heat the sample above Kerr temperature. Another important paper was published by this group in 2005 when they observed inverse Faraday effect. So in Faraday effect, you see the rotation of the beam, polarization proportional to magnetization. But in inverse Faraday effect, they practically induce magnetic field or magnetization using circularly polarized beam. You can imagine that you have circularly polarized light, so left-hand side or left-hand side, you can induce finally magnetization, and then this magnetization depends on the handiness of this polarization of circular polarized beam. And in this case, they used, again, femtosecond lasers, and these oscillations, if you calculate Fourier transform, you finally obtain the spectrum, and it means you obtain, or they here obtained quasi-antiferromagnetic resonance and quasi-ferromagnetic resonance in this dysprosium ferrite. What does it mean here? At high temperatures, there is a antiferromagnetic order. The spins are antiparallelly ordered along x-axis, but there is some tilting angle due to Jalushinsky-Moria interaction. And then you can excite here this quasi-antiferromagnetic mode, quasi-ferromagnetic mode if you have a beam along x-axis and you produce magnetization along that axis. There is weak ferromagnetic moment. So they can observe this such magnons in versus temperature. And so it was, I think inverse Faraday effect was known for many years, but maybe forbidden. And in last 20 years, again, it is used. In this case, the optical pulse is again in visible range. And you can induce magnetic field in pulses up to 5 Tesla. So it's quite strong effect. I will speak about terahertz in field. Means terahertz frequencies are 10 to 12 hertz, and the pumping in our case it will be it is 1 terahertz, and up to 20 terahertz. I will speak about such pumpings, which if you are not familiar with terahertz, it is in millielectron volts. 1 terahertz is 4 millielectron volts. In 2011 was published this paper when they pump the highest frequency phonon, which is around 17 or 17 terahertz, which is just deformation of oxygen cage in perovskite, lanthan strontium manganite. And what they observed, and when they measured change of reflectivity, okay, it is, let's say, 2% change of reflectivity, which is not huge, but from these oscillations, you can again calculate Fourier transform. And you obtain the spectrum of this from these oscillations. And they found that even if they pump it with 17 terahertz, they obtained peak around 1.5 terahertz. And when they pump it at higher frequency, they obtained peak at 6 terahertz. So there was activation of phonons due to nonlinear coupling. The infrared active phonons, due to quadratic coupling, and this is, I think, very important formula, just remember it, take it home. I will use it in many slides. So this quadratic coupling of infrared modes with another mode, which in this case is Raman active mode, with lower frequency. So there is high frequency mode infrared coupling with orthogonal vibration of Raman mode. It can change, it can be activated, this Raman mode, and it can finally change the crystal structure. And it can be responsible for many other cases. And I will show you here. So what happens here, practically you change the potential, which is harmonic without pumping. And with this, due to this quadratic coupling, you get another potential with another minimum, and you can change the crystal structure. And such coupling is not only like this quadratic coupling, but finally you can have also quadratic coupling of infrared or Raman mode with infrared mode, or biquadratic coupling. And later it was even generalized by Dominik Jurasek that you can have trinary coupling of 2 infrared modes with 1 Raman mode. You can change interatomic potential using this pumping. And it can change not only crystal structure, but you can also induce superconductivity close to room temperature. It is a group of Cavalieri who published already a series of papers about such phenomena. And so you know, in Ibakuo, critical temperature is 90 Kelvin. If you have even oxygen deficiency, it will be lower. But what they observed some transient superconductivity here in this concentration of free carriers. They observe even slightly above room temperature. It is, of course, transient effect. It is in picosecond time scale. And what happens here, it's here calculation, coupling of high frequency phonon, again, this against phonon around 20 terahertz is coupled with Raman modes, and here is taken into account there are 10 Raman modes, and how is the coupling, how is it efficient for change of potential, and finally this blue one is the most efficient, and it can produce practically shift of oxygens, and it goes closer to CO or Cooper oxide layers, and then you can enhance the superconductivity. How is it measured? You must imagine it is in picosecond time scale. So it is determined from infrared reflectivity. So again, they can calculate infrared reflectivity, just transient one, and here is a change of reflectivity in equilibrium. Okay, we have no change, and with transient effect, you have just increase and decrease. Why it is like this? In superconductors or in any metals, reflectivity versus frequency looks like this. And so there is a plasma frequency of free carriers, and there is some increase, and here is 100% reflectivity in metals. In best metals, of course, this reflectivity is almost 100% in infrared range, in far infrared range. In bad metals, there is, let's say, increased 20%. And also, the conductivity, optical conductivity, looks like this. This is Drude conductivity and looks like this. Oh, sorry. Yeah. So you have Drude conductivity, and then it decreases close to plasma frequency. But what happens at superconducting phase transition? You have, let's say, the band gap. I mean, energy of pairing of Cooper's pairs. Let's say here, which can be somewhere around 1 terahertz. And then, in classical BCS superconductors, there will be decrease of conductivity at band gap. And then there is no sorry, this should be here. Decrease of conductivity, and then, because integral of conductivity should be constant, temperature independent. So what you lose here is transferred to zero frequency delta function. So integral of conductivity is constant, but there is delta function, so you have infinite conductivity at zero frequency. And what happens in if you have such effect in conductivity? In reflectivity, you will find finally 100% reflectivity below band gap. So you can see effect of superconducting pairing. And this is actually here. You can see such enhanced reflectivity from superconducting pairs. But you can also ask, is it really superconductivity? Isn't it just zero resistivity? So the main evidence is Meissner effect. And it was published last year that it's again by a group of Cavalieri, that they were able to see the Meissner effect in such terahertz pump superconductors. It was observed in more superconductors like this Fulleren system. Again, you have decrease of conductivity and enhancement of reflectivity. I will not speak about it too much, but let's go to ferroelectrics, because many people are here from ferroelectric community. And here is a first theoretical paper about possibility to switch polarization in ferroelectric lead titanate. It is from the group of Rappe, and I will make some experiment here. So what they assume, you know this? I have a oscillator. It is vibration of atoms in this lattice. Let's say vibration of titanium in middle of this oxygen cage, which is responsible for displacement for appearance of ferroelectricity. And what they assume, or what they propose, so we have vibration with some amplitude, and if you will pump it in phase, you can enhance the pumping amplitude, and they assume that you can come from one minimum polarization to another one. If you will not pump it in phase, but sorry, you can stop the pumping because, or you can stop the vibration because if you will not pump it in phase. So this was the idea here. They suggested, let's say, 4 pulses. They suggested 4 pulses. And then they expect that there will be switch of polarization from plus Z to minus Z. And I put it here also, this description, because when you will receive my slides in PDF form, you can study it in more details. And but of course, better is to assume just one pump. And they also calculated that if they will pump it at low temperatures, 50 Kelvin, so they need quite huge electric field, 5 megavolts per centimeter. This is electric field of terahertz pulse. So this is quite huge. If you will be at higher temperature, you can have it at only 3 megavolts per centimeter. And if you will have two pulses, you can reduce this peak amplitude. And it was similarly confirmed in this paper, also very shortly presented by speaker last week. And in this case, this group, again Cavalieri's group, they pumped lithium niobate, which is good ferroelectrics, and they measured second harmonic generation. So you know already what is second harmonic generation. We had a talk about it. And so this blue and red corresponds to polarization up and down. And when they pump it with terahertz frequencies, if they used above 20 terahertz the pulses, they somehow reduced the polarization, but it was not switched completely. But when they pump it with 19 terahertz, they finally got the switching of polarization from plus to minus. And this 19 terahertz corresponds to highest frequency mode, which can be excited by this terahertz. So again, here is this quadratic coupling of infrared modes with another mode, which is responsible for such change of polarization. I have here another paper from literature, 2019, Science. Again, Cavalieri group. They investigated strontium titanate, and they pumped it at different frequencies or different wavelengths and probe it with such beam, and they observed second harmonic generation. Strontium titanate is not ferroelectric; it's centrosymmetric system. I will speak about it more in next slides. But let's say they pump it at low temperatures, but anyway, it's not ferroelectric. But they observed finally two domains in second harmonic generation. So looks like ferroelectric, and what is even, and they explain it yet. Here in this case, the optimal pumping was 17 terahertz, which is again the highest frequency phonon in this strontium titanate. And they explain it such creation of polarization by strain gradient. And if you have strain gradient induced by terahertz pumping, you can have a so-called flexoelectric effect, and due to flexoelectric effect strain gradient, it creates polarization. But I think there is not too much details about such why it here this strain gradient. And but note here one point: they pump it, let's say 20 minutes, and second harmonic generation intensity increased all the time, and then they switch off it, and it remained really half an hour. So it's not picosecond effect like before I mentioned, but it is it remains for long time. And even they observed second harmonic generation after 8 hours, which is quite surprising. Yeah, if you pump it with femtoseconds and you see it 8 hours. My explanation is that when they pump it this higher frequency phonons, they somehow created defects, and they were concentrated in this optical spot, and then these defects create such strain gradient and charges and so on. And it is also supported by their experiment, my idea, that when they illuminated this sample using ultraviolet, then this second harmonic generation disappeared immediately. So ultraviolet, for me, it moves out the defects from this spot, and then you don't see any more gradient of strain, and you don't see such second harmonic generation. In the same issue of Science was published another paper from the group of Nelson, and they again investigated strontium titanate, but they pumped it with single pulse with the peak around 0.7 terahertz. And so they pumped the strontium titanate and probe it at 800 nanometers, and they measured second harmonic generation. And again, they observed a strong increase of second harmonic generation intensity. And if you calculate from this Fourier transform, you see one single peak, which corresponds to double phonon frequency, soft mode frequency, which softens on cooling. And then it splits at low temperatures, probably due to change of symmetry in this system. But it's still controversial result, because there is also another paper claiming that it is not change of symmetry in this case and second harmonic generation due to breaking of centrum symmetry, but it is so-called hot phonon effect. That you practically populate the soft phonons, and due to this, you change the interatomic potential and you generate the second harmonic signal. So it is still matter of debate. Strontium titanate, I mentioned already before. What does it mean? Here, it's not ferroelectric, but it is so-called incipient ferroelectric or quantum paraelectric system. Here is a result of temperature dependence of permittivity versus logarithm of temperature. Note that is logarithm. And there is an increase of permittivity which follows Curie-Weiss law. And if you plot inversion permittivity, you get 0 at 35 Kelvin. And so it looks like that ferrotic phase transition should appear at this temperature. But it's not appearing due to quantum fluctuations. And this paper from Miller is highly cited, and because strontium titanate is source of many other investigations. And by the way, Alex Miller was studying strontium titanate whole life. And by the way, he discovered high TC superconductivity, which was a completely different topic. But strontium titanate inspired him, because if you slightly dope strontium titanate with calcium, you observed superconductivity in such insulating system. You observe it in millikelvin temperature range. So question was, what happens here at low temperatures? Okay, one explanation was quantum fluctuations, and but interestingly, at low temperatures there is tiny peak, which is not quite clearly seen here, but if you plot reciprocal permittivity, there will be at 2 Kelvin some minimum. It means maximum here. And the question is, where is it coming from? Yeah, this effect. And very recent paper from this year is showing that they pumped strontium titanate using terahertz beam generated from lithium niobate, nonlinear optical crystal, and they investigated time-resolved X-ray scattering. They see the diffuse scattering, and from this time-resolved and space-resolved, they can calculate the frequency of excitation, which are seen here, and they observe that transverse optical phonon, it should go to 0 or to some low frequency here, but it's not completely seen at gamma point. It is Brillouin wave vector. 0 is here, and here is acoustic branch. And they observed that there is some coupling of optical branch with acoustic branch at non-zero Q vector. And this, here is even calculations. And this coupling of optical and acoustic branch produces gradient of strain, and therefore there should be some polar nanoclusters. Shown here, yeah, it's a nanometer or 40 atomic unit cell, the clusters, and so you have softening of phonon, which is responsible for increase of permittivity at low temperature, and then some coupling and non-zero Q vector producing such strain. Well, another possibility is how to control magnetization. This group, again Cavalieri, pumped erbium ferrite, and again they excited high frequency phonon, which here is a reflectivity, showing that reflectivity and at this peak it's close to transverse optical phonon. So when they excite this phonon, they observe change of magnetization. This is a weak ferromagnet system, and they could measure this change of magnetization due to magneto-optic Faraday effect or Kerr effect. And what happened here, that they excited two phonons. So they had a polarization of pumping along 110 direction. So they excited phonon along A-axis and along B-axis. And due to this simultaneous excitation, they practically produced movement of atoms along some position, and this movement produces magnetic moment. And again, this effect was explained by, in this case, coupling of two phonons with magnetization. I have not too much time because I would like to speak also about these things, but in dysprosium ferrite was also observed change of magnetic structure. And here is spin reorientation phase transition from weak ferromagnet to antiferromagnetic phase. And when they pumped the phonon, again, there was a possibility to change the antiferromagnetic resonance to down or up this ferromagnetic resonance. But I will skip this. Okay, slightly about bismuth ferrite. Bismuth ferrite is frequently mentioned here. This is also very fresh paper. And they excited a lattice at 17 terahertz and measured second harmonic generation. And when they measured, when the pumping was parallel to probe, they were able to see the change of polarization. This is less than 2% change, but it is existing. And when they pump it perpendicular to polarization, then there is no effect. And important is that when they did not see only change of polarization, it means second harmonic generation generalized by polarization, but also they could see THz-field induced second harmonic generation due to magnetic order, and it is quite strong effect. So using this pumping, you can change exchange coupling in antiferromagnetic phase, and also the strength, the polarization. The measurements was done on single domain ferroelectric and magnetic structure. And again, here was the coupling of this infrared mode with three different lower frequency modes, and you can see influence of each mode to polarization. Unfortunately, some contributes plus, some minus. So finally, you see total is quite small, this change, but it is measurable. But let's go to dynamic multiferroicity. I only 7 minutes, so quickly. Dominik Jurášek from Nicholas Spalding group, they propose that if you will have, let's say, perovskite, and you excite phonons using circularly polarized beam, then the atoms start to move circularly. And this circular motion, this charge, so and this charge is producing current. This current is producing magnetic moment. So yeah, you have this movement and you have magnetic moment. And Jurášek calculated the magnetic moment in different compounds. Here is the list of perovskites, and the strongest effect is expected in strontium titanate and potassium tantalate. This is magnetic moment. It is nucleus magnetic moment. It's not Bohr magnetic moment. But in the case of in this case, I think it was overestimated because they took the phonon frequency quite high and so on. But anyway, again, I skipped I already shown here magneto-optic Kerr effect. What is important is using this pumping, this time dependence of magnetization generated by circular polarized beam should be like this, and because if you have double degenerated phonon, so this omega minus should be 0. So finally, you can remove it, and you will measure. You should expect magnetization if you do Fourier transform. The magnetization should be at 0 frequency, so static magnetization, but transient, only in picosecond time scale. And the experiment was published first time last year by Massini. And she observed Kerr rotation. It means magneto-optic Kerr effect in reflection. And so it was single pulse measurements at room temperature, pumping with 3 terahertz. And she observed such oscillations. And when she calculated Fourier transform, she obtained 2 peaks at 6 terahertz, which is twice pumping frequency, and 0.5 terahertz. Nothing at 0 frequency, but when she calculated this magnetic induction due to movement of atoms, she decomposed this effect to magnetization effect and also to electron and ionic Kerr effect, which are these oscillations. So these oscillations are responsible for this peak and also this second peak due to optical rectification, and the magnetization should be this red curve at 0 frequency. But it is not exactly seen directly, and the problem is that this 3 terahertz pump is quite broad at 3 terahertz. And we decided to measure potassium tantalate because it is cubic down to lowest temperature. It is very similar to strontium titanate. Again, permittivity is growing up at low temperatures, and we can come to resonance with the soft phonon. This increase of permittivity is due to phonon softening. And so we pumped this phonon at low temperatures. And we used free electron laser in Dresden, which is a large-scale facility, and it has optimal energy, pulse energy around 0.7 terahertz with strongest intensity. And so we pumped potassium tantalate and measured rotation of this beam, optical beam, and saw this Faraday effect in transmission mode. So when we had a left-hand circular polarization, we see such peak here. I have to stress, our pumping was not single pulse, but it was 10 picosecond long. So then we have relaxation. So here is increasing signal, and then we have relaxation. But when we use signal plus, it means right-handed pumping, you can see the change of sign of this rotation. So it is evidence for magnetic induction in this case. So usually to remove some effects of non-magnetic contribution to Faraday rotation, people calculate sigma plus minus sigma minus, and so we obtain such Faraday rotation, independence on temperature, and Fourier transform gives us again peak at 2 pumping frequency. I forgot to mention pumping is at 0.7 terahertz. And then, so this is again this electro-optic Kerr effect, but here we have increase of amplitude, and this is plotted better here at low frequencies, and we see increase of intensity on cooling when we come to resonance, in resonance with the soft phonon. But when we are out of resonance, we still see some intensity. So I think this is not magnetic response, but this difference is magnetic response. And we measure as well electro-optic Kerr effect. It means this birefringence, which should be quadratically dependent on electric field. And again, we see the pumping peak here, and here increase, which reminds me here as well, but it is much weaker. So this electro-optic Kerr effect is much weaker, and this difference is due to magneto-optic effect. I think I should. I have still time. I hurry so much. Okay. I was thinking that I should finish already. Okay, just to see that that we have a same effect like Martina Bassini published in strontium titanate. We asked her to measure it as well at room temperature with pumping 3 terahertz. And what you see here is pumping with right-handed blue, left-handed yellow, and linear pumping. This is Kerr effect. Linear this electro-optic Kerr effect we obtain with EF pumping linearly. So there is much weaker signal. But if you have sigma plus minus sigma minus, it means you subtract right and left-handed pumping. We have such signal at 3 terahertz at room temperature, and again we see double peak, same like was observed in strontium titanate. So again, here is the effect that they don't see classical peak at 0 frequency, but they see peak at 0.5 terahertz here as well, and this is due to optical rectification of broader pumping field. And this can be pumped with 3 terahertz because at room temperature the pumping or this frequency of soft phonon is already okay. At 300 Kelvin should be the phonon frequency around 2.5 terahertz. So we are close to the soft phonon frequency. And when Martina pumped this strontium titanate at different temperatures, again with 3 terahertz, you can see decrease of magneto-optic Kerr effect, and because you are coming out of resonance, because the soft phonon at 100 Kelvin has a frequency around 1.5 terahertz. So but when she heat up the sample, the intensity of both peaks is increasing because the soft phonon above room temperature, it will be 3 terahertz around 400 Kelvin. So we will come to the best resonance around 400 Kelvin. When we measured it at 100 Kelvin, pumping with 3 terahertz is a weak signal, but if you pump it with 2 terahertz, it's much stronger signal. Again, it corresponds to this, that if we are at 100 Kelvin, we are close to 2 terahertz, and we can see this magneto-optic Kerr effect. Question is, how large is the magnetic moment? theoretically, it was here calculation of Michel Damac from Paris. This time response should look like this. This is calculated just if you take into account eigenvector of the soft phonon and its derivation of displacement. So, but note this magnetic moment should be order of 10 to minus 5 of Bohr magneton. It's very weak effect theoretically, but actually Martina showed in strontium titanate that this orbital magnetic moment is 10 to minus 1 Bohr magneton. So this is 4 order of magnitude larger, which is very surprising effect. And it was there is a series of papers speculating this explanation, and I think most possible is the explanation that there is a coupling of phonons, phonon vibration moment, magnetic moment, with electron shell of around these atoms, and because mass of electrons is 10,000 smaller, then you have 10,000 times higher magnetic moment, and therefore you finally observe such enhancement of magnetization due to phonon pumping. There are also other papers from Berlin claiming that there is activated some non-Maxwell field. It means field which has a symmetry like magnetic field, but it's not magnetic field. And this can be responsible for such enhancement of magnetic moment. We measure as well second harmonic generation, THz-field induced in strontium titanate at low temperatures. We see the effect, but it will be probably better to explain it by this hot phonon effect. It's still in progress, this paper. But it can be also mentioned that second harmonic generation in potassium tantalate was also measured classically in crystal. There is very weak signal in zero electric field showing very weak signal at low temperatures, but if you apply electric field, note it is multiplied here 350 times. So the effect is, the intensity is very low, but it is present here, and it can be maybe explained by presence of polar nanoclusters in potassium tantalate, again with such effect like in strontium titanate when you have coupling of optical branch with acoustic branch, which produces theoretical minimum at non-zero Q vector, and it produces finally some modulation of polarization and creation of polar nanoclusters due to flexoelectric effect. You can ask how we can use it. Yeah, I have to stress that this magnetization in strontium titanate, potassium tantalate, is of course transient effect. It remains here only in picosecond time scale. But it can induce strong field. And last year was published this Nature paper when they pumped phonons in substrate like sapphire or silicon dioxide or silicon dioxide. And on the top they had ferromagnet. And they see that when they pump the phonons, here is they can practically, if they are in resonance with phonon frequency, here is a moment, red is absorption. So when you have a maximum absorption, you should be close to phonon frequency. And if you are close to phonon frequency, you are able, or they observed, switching of magnetic domains in this ferromagnet. So you can see here such, without pumping, there is homogeneous ferromagnetic order, And when they pump it, they observed opposite magnetic domain. And it can remain, of course, long time because you switch the magnetization. So using pumping of phonons in substrate, you should be able to switch magnetic domains in the thin films, which can be used finally in electronics. And the point is that you can switch it very quickly. This in picosecond time scale or sub-picosecond time scale. And another theoretical prediction, again from Jurasek, is about cerium trichloride. He predicted that if you pump the phonons in this system, you should be able to induce internal, effectively, magnetic field of order 100 Tesla, huge, just by pumping of phonon. Again, due to spin-phonon coupling, because in this case you have rare earths, cerium, and also this crystal field, and finally it can induce really huge magnetic field. Okay, 100 Tesla I don't trust because they assume, I don't know, 10 megavolts per centimeter amplitude of electric field in terahertz. But it can. But there is another paper studying cerium trifluoride, and they observed magnetic field 3 Tesla. So it is also strong effect. And this prediction that it can be valid is also supported by observation of splitting of Raman active phonons in magnetic field. And classically, if you have system, magnetic or ferroelectric, does not matter. The splitting of phonons does not appear in magnetic field. You can maybe shift it. You can have magnetoelectric effect. You can shift. You can change the permittivity, and you can have a tiny change of phonon frequency. But in this case, there is a splitting, and it's order of half terahertz, so it's huge. And in this paper, they predicted that it should be as well seen this splitting in infrared active mode, and we just recently measured it, and we observe it as well. So some phonon around 5 terahertz, so around this frequency, is split about 0.4 terahertz in magnetic field. This is paper quite old, 1978, but still valid. Well, I'm coming to conclusion. I wanted to give you some overview what can be done with electromagnetic radiation. Okay, you can burn the sample, you can demagnetize it, but you can as well change the magnetic structure using magnetic field, using terahertz electric field, and you can induce superconductivity close to room temperature, which is amazing. You can switch the ferroelectric polarization. You can increase the antiferromagnetic vector in bismuth ferrite and also increase spontaneous ferroelectric polarization in this bismuth ferrite. But what is also interesting that you can induce magnetic moment in diamagnetic systems. So in the case, there is no magnetic ion, but just due to pumping of phonons and creation of chiral phonons, or circularly polarized phonons, better say, you can induce the magnetic moment in such system. This is all. Thank you for your attention.